Okay, so how do we monitor, or how do we maintain and service and inspect oxygen systems? What can we expect there? Okay, bleed air is often used to heat the cabin whenever there's not another option for heating available. And the way this happens is that you take bleed air off of the engine and you mix it with cool outside air, and that through a series of valves and then ducts that eventually deliver it to the passenger itself. Pretty easy solution. You just take the bleed air, which is super hot, the cool outside air, and then you open a valve with more outside air than bleed air, and that lowers the temperature through that mixing valve to a comfortable level inside of the cabin. Now, this is the bleed air system on a 737 MAX. Now, the 737 is probably not the best example of bleed air heating because it has so many other options, but this kind of goes to show you how robust bleed air actually can be. And so, like, they use it on the 737 for engine starting, air conditioning packs, thermal anti-ice system, hydraulic reservoirs, potable water system. All those different systems all leverage bleed air, and a lot of it, like for especially for like anti-ice, is because the bleed air is hot and it's highly now. There's two main things to take away from bleed air. One is that there's a mixing valve that takes the hot bleed air and mixes it with cool outside air. And this, in particular, graphic with the old LEAP engines on the 737, they call it a pre-cooler heat exchanger, is what we're calling the mixing valve. But effectively, it does the same thing. All it's really going to do is put the two air masses together. There's an overboard vent off to the side, and the rest goes to different places in the aircraft. Now, the other one to think about is that like bleed air is also can be responsible for a lot of fires. So these are something you want to take into account and remember. So you have overheat heat sensing elements near all the pneumatic ducts, and they monitor the system duct for leaks because the leak on a bleed air system is what's going to cause your fire. Now, there's also an automatic over temperature and overpressure protection system that will flag any abnormalities to the cockpit. And there's also pressure transmitters and even a gauge on the P5 panel in the 737 that show the right and left different manifold pressures. And that's even though that in particular little tidbit's not necessarily standard across all aircraft. What is fairly standard is that if you're using bleed air for anything, you're going to be able to read it in the cockpit somewhere. And most of the aircraft that use bleed air for heating are actually fairly sophisticated. It's not gonna You're not going to run into like a 172 that has like bleed air heat. They have like other types of heating, which is kind of similar in a little ways, like exhaust heat exchangers and things like that. We're going to talk about here in a minute. But effectively, they're like bleed air, but they're not bleed air, so they don't have near the level of sophistication, so you don't have to worry about it. This is mainly going to be for turbine aircraft, and especially the bigger you get, the more bleed air is going to play a part because it's basically a more efficient use of power. You're already burning the gas to turn the turbines to compress the air. You might as well use it for something else useful rather than having a whole other subsystem that pulls a whole new type of resources, like say like electric heat or something like that would take a lot of battery power, a lot of electric power, and then you'd have to have a whole other sea of components. Bleed air is just a lot more efficient. That it's already there and it's already being produced. We might as well use it. Let's say you don't have a bleed air system like we just looked at. Let's say that you're flying in a Cherokee 140 and you want to turn the heater on. Or even better, if you're flying doors off in a Cessna 170 like I was in late October back from Dallas, and the weather had changed and we didn't realize that it was about to change and it got really cold. What do? You'll turn on the heater, but inside of a small piston aircraft, what does that heater look like? It's a combustion heater. Now, what does that mean, and what can we expect from combustion heaters? Aircraft combustion heaters are used in a lot of small and kind of medium-sized aircraft, and they provide a heat source that's independent from the aircraft's engine, but it still uses fuel from the main fuel tank, so it can be kind of confusing. It's using combustion, but it's generating its own combustion, not using the combustion that's happening right in front of it. The source of the heat in this case is an independent combustion chamber and is located in the cylindrical outer shroud of the heater unit, and the exhaust from the combustion is funneled overboard. Now, our blower ensures that the correct quantity and pressure of air are sent into the chamber, and this is a an example of a modern combustion heater. There's a lot of old ones out there, but this is one that is delivered by Janitorial Aero, and they have a little good graphic that kind of like outline the different parts and pieces. So you have a PMA blower that actually moves the air from the around the combustion chamber and into the aircraft. There's an igniter with a spark plug that goes on there, very similar to kind of what happens in the engine. You have a high output ignition that'll spark electric, and then you have your all your different switches and solenoids and all the electrical components that happen around trying to electrically start a fire effectively, and then blow the excess hot air into the cockpit. All right, this graphic just shows you how a combustion heater works, and so there's really not a good way to get after it to explaining this because there's kind of a lot happening at the same time. So we're just going to take it. We're going to follow the fuel, and then we're going to follow the air. Right. So the fuel starts off in the aircraft fuel tank. It goes through a filter, and then it's being drawn in by a pump that then goes to a relief valve. Then that solenoid valve is what turns the fuel on for the combustion heater. It then goes into fuel control assembly. We won't really get into that. It's just more fuel management. And then eventually gets piped down into a spray nozzle. All right, and that spray nozzle it gets ignited. And that's what actually causes the combustion, and then the combustion simply just goes outboard. Like you have a big fire that's going on, and off you go. So imagine kind of like a jet engine, but without all the turbine stages. It just you have a little explosion, and off on its way. Now the air. It can go on the left-hand side of the graphic on the very bottom, and you'll see this thing called a ventilating air scoop. So that's the air that comes in from the outside of the plane. So it's kind of pressurized air that comes in. You have a blower that then speeds it up and pushes it down to where the combustion chamber is happening. But the combustion chamber, the air chamber, and two different chambers, I guess. The air is going to then go around the combustion chamber, pick up that heat, and then go out into heated air, and they have an exhaust shroud for any air that's not being used. So let's say if you have the heater on, but you want to close the vent, 90% of the way, 90% of it's going to end up going overboard, and 10% of it comes into the cockpit to try to get the right heat or right temperature that you want on board. Now that's just kind of the basic thing. It's not really that complicated when you look at it. It's basically like any of those little bullet heaters that you might see in a hangar or maybe a construction work site. You're just burning gas to produce heat, and then you're mixing cool air with it to bring the heat down. So that way you can dial in the temperature that you want inside of the cockpit. These are really, really effective, and they work really well. And you'll see them not on your kind of your lower end aircraft, but your medium, your Bonanzas, your Aztecs, those types of things. That's where you'll start to see a lot of these combustion heaters. All right, and here's an example of one that's actually installed on an aircraft. They're typically right there, kind of forward of the nose gear and engine compartment, that kind of area. This one is mounted horizontally. They can also be mounted in line with the aircraft. So you'll never see them. I've never seen one really stand up on its end. But you can get them sideways like that. That's a pretty common mounting approach. And they're also, you can get them to where they are stood up to where the air intake is actually in the front, and it kind of rams air into it, makes it a little bit more efficient. These they're fairly reliable. You'll end up having to do some maintenance on them. There's a counter you can see on the top right hand side of the picture where that's going to give the hours for that combustion heater, and so likely on annuals you probably have to look at that and see where it's at, and then do the maintenance that is required. Other maintenance of combustion heaters consists of just routine items like cleaning filters, checking spark plugs for wear, ensuring the inlets aren't plugged, visual inspections, all that good stuff. All maintenance inspections of combustion heaters should be accomplished in accordance with the aircraft manufacturer's instructions, and that's 100% the case on everything, but especially on these because they're all somewhat unique. They all do the same thing and in the same way, but their construction could be a little bit different from heater to heater. So, very important to just simply follow the manual. Whatever the manual says, that's what you do. What about an exhaust heat exchanger? What is that, and how does it work? Okay, by far and away the more common approach to heating an aircraft, especially small aircraft or the less expensive, less fancy aircraft, is going to be exhaust heat exchange. Now that can look a bunch of different ways. We're going to give you kind of the basics, so that way you can apply it outside of this. But essentially, all that's really happening is that the engine is going to run, it's going to get hot, and then you're going to open up a vent that allows for ram air to come in, blow over the tops of the exhaust where the majority of the heat's at, and then blow into the cockpit. Now, the good part about this is that it's super simple. There's very few moving parts, and the parts that are there, it's literally just kind of a really stiff wire that opens and closes the door, maybe some springs and like a little slider control. It's no different than say in your car, especially older cars. This is a thing. Like you notice that you can't get the car warm until the thermostat opens and you start to see the little needle move on your engine temp. And this is why is because you have an exhaust heat exchanger system on board your car, and the engine has to get warm enough in order for that heat to be coming from somewhere, anywhere. And that's exactly how this works. Now, the downside is, and this is something that you'll have to pay attention to on any annual you do, is that any crack in that exhaust heat system could put exhaust into the heat that's coming into the airplane. Now, that means that it's any air coming into the airplane at all. Even if the door is shut, it's not necessarily sealed or anything like that. So even during the summertime, you could be getting some of that warm air start to blow in. And if there's exhaust in it, that means there's carbon monoxide in it, and that means that you can kill people if you miss a exhaust crack somewhere in there, and it's very prone to cracking. And so this is something you want to pay attention to, so that way you can catch it before it kills somebody. And you'll see multiple ADs will come out looking for exhaust cracks. You'll see like any time that this setup is being used, the FAA particularly is going to be very, very, very keen to make sure that people are protected from it, and that's usually done via inspections during the annual inspection. That being said, this is actually, the good side of it is it's extremely effective. It will. I just got back from Cloquet, Minnesota, which is like right up on the northern Canadian border of Minnesota, and it was super cold, and we were flying around with the heat on in the aircraft, and it was perfectly fine. Like I took my jacket off. I wasn't running around in a t-shirt and having a grand old time inside of the airplane, and we didn't use combustion heaters or anything else, just simply exhaust heat, and it did perfectly okay, even in freezing conditions. So these are really effective. You just have to be really aware of the status of your exhaust manifold, flanges, all that good stuff, or else you could actually give somebody carbon monoxide poisoning. And we've already learned about carbon monoxide poisoning in our fire systems class, but this goes to show you like the importance of carbon monoxide detectors inside of the cockpit, especially if you can position it so that way they're close to where the heater ports are. That's what's going to give you the earliest indication that there's carbon monoxide coming into the cabin. All right, and this is just an example of a low-wing aircraft and the different heater ducts that you could potentially get with an exhaust heat exchanger, or even a combustion heater. Either way, it's just the way that air typically will move in the cabin. So a couple things to note: your defrost that goes up on your windows is super important, because without it you can't see. And most flights are actually visual flight rules, VFR flights, and so you've got to be able to see. And even if they're IFR rules, you're still going to be able to see to get the plane on the ground. So that's how exhaust works. Now, typically, it's going to work exactly like that. There's going to be a duct that comes up and just blows hot air over the top of the windscreen, and that's going to remove any kind of fog or any sort of obscuration from the field of view of the pilot. Now, other things to note: notice that there is a fresh air inlet in the tail. This is really common. What that does, the air is going to blow down and into the cabin. So, like if you remember sitting in an airliner and you are able to turn the knob on above you and it blows air on you like that. Well, on a small airplane, you don't have a pack or any sort of any sort of device to actually blow air on you unless it's equipped with an air conditioner, and so this helps compensate for that. And it helps move air through the cabin, so that way you don't get this like stagnant hot air sitting there. So as long as the aircraft is moving forward, generally speaking, you get some air that's blowing out. Now all that air has to go somewhere, and so typically you'll have ducts on the bottom that vent overboard. So you have like you look at item number 5, you have like a cabin air exhaust that eventually it'll go overboard and be gone. So that way, that the hot air that's in there can be pushed out, and the cool air can come down. And you can also typically close some of those up if need be. But generally speaking, you want air flowing through the cabin if at all possible. And you even do that with pressurized aircraft. The difference is that you have an outflow valve, and that the air that's coming in is like super high pressure, and the outflow valve just opens and closes to help keep the pressure where it needs to be. Either way, that's how the air flows through the cabin. Now your heater is typically going to be in the floors like that, and they're going to come up because heat rises. So you're just using the natural convection and physics of hot air to your advantage. Now, I'll tell you, from a maintenance standpoint, these things crack really bad on a regular basis, or get torn or whatever. They're just susceptible to all kinds of wear and tear, especially the older they get. If you work on anything that was built in, say, like the 60s and 70s, which is a lot of the GA aircraft, and they have those hard plastic vents on there, I'll caution you, if you can at all possible, never take them out, because they're going to be brittle and they're going to want to fall apart in your hands. And then once you get one starting to fall apart, it gets very difficult to put them together, and they're hard to come by these days. Most people I know that are replacing them are actually getting them 3D printed and put back in the aircraft, and they're made out of ABS plastic, so they'll last a lot longer. But either way, that's kind of unnecessary details. But that's how air flows through a small aircraft. Now, as you scale up, they're going to be similar in a lot of ways. It's just going to get more complicated with more robust systems that are more effective at doing this. But that's the kind of bare bones skeletons of how heat and fresh air move about an aircraft. Especially around here in July and August, if you set an aircraft out there on the flight line that jet's tied down back there, you're going to get into that airplane and you're going to know the meaning of heat. It's going to make you pass out to the point where it is literally dangerous inside to stay there for a long period of time. So what do we do for the passengers and for ourselves? There are things known as packs. So what's a pack and how does that work? Okay, air cycle air conditioning prepares the engine bleed air to pressurize the aircraft cabin. Now, if you just put regular bleed air without any sort of prep, it would be extremely hot inside of that airplane. So something has to happen in order to make it tolerable. The temperature and the quantity of the air must be controlled to maintain a comfortable cabin environment at all altitudes and on the ground. The air cycle system is often called the air conditioning package or pack. It's usually located in the lower half of the fuselage or in the tail section of a turbine-powered aircraft. Now, I will tell you that most aircraft have two, and both of them have to be working for the aircraft to be used for any sort of operations with passengers. A pack being out will absolutely ground an aircraft because those airplanes get so hot on the ground. It could even be like not really that hot outside, but just by virtue of sitting and baking in the sun and the way that they're built, they will get unbearably hot just sitting there. And it's very, very dangerous to put like grandma on there who's already kind of like physically compromised just by virtue of her age into like a 104-degree fuselage where she's just going to sweat herself to death. And airliners don't want that liability whatsoever. And nobody really wants anybody to pass out or anything because of the heat. So this is how they generally will work. You have a bleed air mixing valve that's going to come in. It's going to then pipe it into the refrigeration system, just like you would at your home HVAC system. Matter of fact, these are not really that dissimilar. Something I always like to kind of point out to our HVAC people who they get all hot under the collar that they think they're wizards at electricity, and then I like to point out that the things that we work on has two of all theirs, and it's just a subsystem. So it's always kind of a fun little rivalry right there. But this is the air. This is a pack. This is a pack off of a 737, and there's two of them. There's one on either side of the belly. That they have to run in order for us to be able to move passengers from point A to point B. Okay, and then here's kind of a systems overview of how the heat exchanger or the air cycle conditioning system on a 737 works. Notice you have two primary air inputs. All right, so you have your bleed air that's coming in. It's hot, and it could be from the EPU. It could be from engine 1, engine 2, or whatever. In this particular situation, we're saying it's engine 2 per the graphic. That hot air is going to come onto the system. Now, that's air source number 1. Air source number 2 is just ram air, just like it would be in an exhaust heat exchanger. It's going to come in there. And then once you open the pack valve, the hot air is going to come in, and it's going to mix with the ram air. Now, some of that is going to go overboard. Actually, the majority of it's probably going to go overboard because it's taken in so much. But some of it is going to get piped into the system, where it's either going to come into the air mix valve or it's going to go right to the compressor, one of the two. Those will then come in and then get cooled until it's extremely cool, and then there's going to be a mixing chamber that takes straight bleed air, and then it puts it together in that mixing chamber, and then it pipes it out to the manifold that's going to take it throughout the rest of the aircraft as conditioned air. And so you have all these different types of air that's coming in, but essentially all that's really happening is the same types of things that are happening with your exhaust heat exchanger, except for in this situation, you have cold air that's being produced, that's being mixed into the bleed air to get kind of like a middle ground somewhere that people actually, air temperature that people actually want to be a part of. All right, this is the heart of the air cycle air conditioning system. It's known as the refrigeration turbine unit. It's also known as the air cycle machine, or ACM. And this is one from a 737 NG, and that is an ACM. Okay, it's comprised of a compressor that's driven by a turbine on a common shaft. The system airflows from the primary heat exchanger into the compressor side of the ACM. As the air is compressed, its temperature rises. It's then sent to a secondary heat exchanger, similar to the primary heat exchanger, located in the ram air duct. The elevated temperature of the ACM compressed air facilitates an easy exchange of heat energy through to the ram air. The cooled air system air, still under pressure from the continuous system airflow and the ACM compressor, as exits the secondary heat exchanger, is then directed into the turbine side of the ACM. The steep blade pitch of the angle ACM turbine extracts more energy from the air as it passes through and drives the turbine. Once through, the air is allowed to expand at the ACM outlet, cooling even further. And the combined energy loss from the first air driving the turbine, then expanding at the turbine outlet, lowers the system air temperature to near freezing, which is then remixed with bleed air to bring it back up to 70 degrees or whatnot that's actually tolerable to the passengers. Okay, another component that's essential to success of the air cycle system is the water separator. Effectively, cool air from the air cycle machine can no longer hold the quantity of water it should whenever it warms. So it basically squeezes that because all those molecules are coming together so tight that it starts to squeeze whatever water is being held by the air out. So a water separator is used to remove the water from the saturated air before it's sent to the aircraft cabin. If not, you get all kinds of crazy fog and all kinds of problems. The separator operates with no moving parts. Foggy air from the ACM enters and is forced through a fiberglass sock that condenses and coalesces the mist into a large water drop. And the convoluted interior structure of the separator swirls the air and water. The water collects on the sides of the separator and drains down and out of the unit while the dry air passes through. A bypass valve is incorporated in case of a blockage. All right, now this is the air cycle system or air conditioning system on a 737 MAX. Now, the air conditioning packs discharge into the mixed manifold of the distribution system. Air conditioning pack discharge is used for these purposes: supply fresh air to the cabin at a comfortable temperature, pressurize the airplane, cool the electronic equipment, and then heat the cargo compartments. So it's got a lot of different functions, but if the pack's out, you're not going to be able to keep grandma cool, pressurize the plane, or cool your avionics, which the more avionics we get, and we're going to get to this here when we get to instrument cooling, the more the avionics are in the aircraft, the more important it is to keep them cool. And so this is a vital piece of equipment that goes under the aircraft. It's notice that you control it on the P5 module, so that's your overhead panel above the pilots. But then you have two boxes down in the eBay, the IAC, the Integrated Air System Controller, and then the Air Conditioning Accessory Unit Controller, so the ACAU. Now, though the ACAU is going to control your TCV valves on either place, as well as a few other valves to help distribute that air as needed. The air system controller is what's going to actually control your packs and all that. So just know that whenever you go to start troubleshooting it. But from what I've seen, and I really, to be honest, I have not really messed around with these that much. The problems that end up happening are usually like stuck valves, broke motors or whatnot. That kind of basic type thing. Not really super duper complicated to work on, but really important because if you don't have a working pack, it's going to be bad for everybody involved, to include the black boxes in the eBay. You'll notice that those the eBay has instrument cooling that comes up into it that's supplied by Pack 1, Pack 2. And if you pull a box out while the aircraft's running, there'll be little holes that sit underneath it that blow air up into it. It feels like kind of like an air hockey table. So that's how important the packs actually are to just keep everything working copacetically. Never mind the fact that you also don't want grandma to pass out because it got too hot. But yeah, that's air conditioning on a 737 MAX. All right, let's go over like the vapor cycle system and talk about how that works for a legit air conditioner that's on board. All right, before we really get into the depths of the air conditioner and all that good stuff, we need to understand how it works on a theoretical level. So let's just talk a little bit of the theory of refrigeration. So energy can either be created or destroyed. However, it can be transformed and moved around. This is what occurs during the vapor cycle air conditioning. The heat energy is moved from the cabin air into liquid refrigerant, and due to the additional energy, the liquid changes into a vapor. The vapor is then compressed, becomes very hot, and is removed from the cabin where the very hot vapor refrigerant transfers its heat energy to the outside air. And in doing so, the refrigerant cools and condenses back into a liquid. The refrigerant returns to the cabin to repeat the cycle of the energy transfer. All right, now the temperature at which a substance changes from a liquid into a vapor when heat is added is known as its boiling point. This is the same temperature at which a vapor condenses into a liquid when heat's removed, and the boiling point of any substance varies directly with pressure. So when pressure on a liquid is increased, its boiling point increases, and when pressure on a liquid is decreased, its boiling point also decreases. For example, water boils at 212 degrees Fahrenheit at normal atmospheric pressure, and when pressure on a liquid is increased by 20 psi, it doesn't boil at 212 degrees. More energy is required to overcome the increase in pressure. It boils at approximately 226 degrees. The converse is also true. Water can also boil at a much lower temperature simply by reducing the pressure upon it. With only 10 psi of pressure upon the liquid, it boils at 194 degrees. Now, vapor pressure is the pressure of the vapor that exists above a liquid that is enclosed container at any given temperature. The vapor pressure developed by various substances is unique to each substance, and the substance that is said to be volatile develops at a high vapor pressure at a standard day temperature. This is because the boiling point of that substance is much lower. The boiling point of tetrafluorine ethane, or R134A, the refrigerant that is used in most aircraft vapor cycle air conditioning systems, is approximately negative 15 degrees. Its vapor pressure at 59 degrees is about 71 psi. The vapor pressure of any substance varies directly with temperature. All right, so let's just walk through the vapor cycle. If you look at this graphic, it actually begins with the receiver dryer. So that's where the R134A is filtered and stored under pressure in the receiver dryer. The refrigerant is in liquid form, and it flows from the receiver dryer through the tubing to an expansion valve. And inside the valve, a restriction in the small form of a small orifice blocks most of the refrigerant. Since it's still under pressure, some of the refrigerant is forced through that orifice. It emerges as a spray of tiny droplets in the tubing downstream of the valve, and the tubing is coiled into a radiator type assembly known as an evaporator. A fan is positioned to blow the cabin air over the surface of the evaporator, and as it does, the heat in the cabin air is absorbed by the refrigerant, which uses it to change the state of the liquid to a vapor. So much heat is absorbed that the cabin air blown by the fan across the evaporator cools significantly, and it can actually turn into a block of ice if you're not careful. This is the vapor cycle conditioned air that lowers the temperature in the cabin. Now, the gaseous refrigerant exiting the evaporator is drawn into a compressor. There, the pressure and the temperature of the refrigerant are increased. The high pressure, high temperature gaseous refrigerant flows through a tubing to a condenser. Now, the condenser is like a radiator comprised of a great length of tubing with fins attached to it to promote heat transfer. Outside air is directed over the condenser, and the temperature of the refrigerant inside is higher than the ambient temperature, so heat is transferred from the refrigerant to the outside air. The amount of the heat given off is enough to cool the refrigerant and condense it back into a high-pressure liquid, and it flows through the tubing and back into the receiver dryer, completing the vapor cycle. There are two sides of the vapor cycle air conditioning system. One accepts heat and is known as the low side, and the other gives up heat and is known as the high side. The low and high refer to the temperature and pressure of the refrigerant. As such, the compressor and the expansion valve are the two components that separate the low side from the high side of the cycle. Refrigerant on the low side is characterized as having low pressure and temperature, and refrigerant on the high side is said to have high pressure and temperature. All right, so we won't go over most of the parts of the vapor cycle system, simply because you've seen it all before. You've seen valves, you've seen heat exchangers, you've seen pumps, and even condensers, just a grand pump with a big chamber on it. But like one thing that you haven't yet seen is the filter dryer, and it's because it does something that's kind of unique. It's going to take the R134 from the condenser, and then there's going to be a desiccant in there that basically removes any of the water vapor that could potentially be in there, because this is a system that you want no water in whatsoever. And then once it goes through that, it'll filter it, push it back into channel, and that will go into the expansion valve. Now, these are actually pretty common that you'll see go bad or whatever, and the reason being is that it's basically just a glorified filter. It's a water filter, and so these are the things that you'll have to change out on a regular basis, and that even goes for your home HVAC system. These are one of the things that routinely go bad, and you have to end up fixing. Okay, the vapor cycle air conditioning system on a Cessna Mustang, which this is showing, has two evaporators, one for the flight deck and one for the cabin. And each evaporator assembly contains the evaporator, a blower, and a thermal expansion valve, and a temperature feedback line from the outlet of the evaporator to the expansion valve. Now, I'll tell you that you won't see a true blue air conditioner on a heavy commercial aircraft, generally speaking. These are going to be more for your business jets that they have to get the aircraft running and then prep it to receive passengers before they crank the engines and all that stuff. And they may not have the air cart that, or like a hover cart, they can hook up to the plane like you do at a gate before you get pushed back. It's just kind of a efficiency thing for the airlines to just rely on the packs and then rely on their ground crews, as opposed to business jets, or say like high-end general aviation aircraft. Like I've worked on a Cessna 206 that has a air conditioner on there. The reason why they have their air conditioners is because you don't have any of that support, and so if you're going to try to get in the aircraft and cool it down, especially if it has a lot of avionics in it, you're going to want something to cool it down that's probably separated from the engine, that you could turn on with just electric power and run it just like you would an air conditioner like at your house, and that's where these start to come in. That being said, is that you generally won't work on them just a whole lot unless you're in that world. Now, a pack you'll work on a pretty regular basis with the heavy commercial stuff, but it just operates a little bit differently. You don't necessarily have to worry about the refrigerant side of it, whereas you do it with business jets, high end general aviation aircraft that are trying to keep cool. But that's the vapor cycle. All right, just like any other special system, you're going to have special tools to service that special system. In our case, we have what's called a manifold set. So this has been the main servicing device for the vapor cycle air conditioning systems for a long time. It contains 3 hose fittings, 2 O-ring sealed valves, and 2 gauges. And it's essentially a manifold into which the gauges, fittings, and valves are attached. The valves are positioned to connect or isolate the center hose with each fitting, and hoses attached to the right and left manifold set. Fittings at the other ends of these hoses attached to the service valves in the vapor cycle system. The center fitting also has a hose attached to it, and the other end of this hose connects to either a refrigerant supply or a vacuum pump, depending on the servicing function to be performed. And all servicing operations are performed by manipulating these valves. This really is kind of the heart and soul of the vapor cycle, technician that's working on it. You've probably seen these guys working on your home AC with the manifold set just like this. Now, these gauges on the manifold set are dedicated, one for the low side and one for the high side. The low pressure gauge is a compounded gauge that indicates pressure above or below atmospheric pressure. Below atmospheric pressure, the gauge is scaled in inches of mercury down to 30 inches. This is to indicate a vacuum of 29.92 inches of mercury equals an absolute vacuum. Above the atmospheric pressure, gauge pressure is read in psi. The scale typically ranges from 0 to 60 psi, although some gauges can extend up to 150 psi. The high pressure gauge usually has a range from 0 up to about 500 psi gauge pressure. Okay, so R134A comes in containers measured by the weight of the refrigerant they hold. Small 12-ounce to 2.5-pound cans are common for adding refrigerant. Larger 30 and 50-pound cylinders equipped with shutoff valves are often used to charge an evacuated system, and they're used in shops that service vapor cycle systems frequently. So basically, the shops that do this kind of thing will have very large, 134A reservoirs to service from. Everybody else just kind of gets these little cans to do any kind of one-off servicing that they end up having to do. Larger cylinders are also used in full servicing carts we've seen before. The amount of refrigerant required for any system is measured in pounds, so that's something to remember. Manufacturer service data, and you charge the system to the level specified only when approved refrigerant is from a known source. So you don't get don't be pulling it from one plane to put in another plane or anything else like that. Also, in order to handle this, you're going to have a EPA certification. We at the school currently don't offer that, at least on the aviation side. Now, you can get it on the HVAC side. Not that big of a deal. It's basically just like, hey, don't vent this stuff to the atmosphere. Reason being is back in the day, there were guys that would work on this type of stuff, and they would just open it up and just let it blow all out of the system, and that is one of the things that really depleted a lot of the ozone layer. As cliche as that may sound, that was a serious problem back in like the 70s and 80s, and so enforcement came in, and then eventually they started trying to come up with a new refrigerant that didn't have the same sort of effect. And that's how you get our 134A. Now, the downside is they've ramped up the price of all that refrigerant significantly in doing so. Luckily for us in aviation, we don't have to mess with it that much, so it's not usually that big of a deal. But those are all just kind of like little background information for the R134A. It's kind of an oddball chance that you'll actually end up using this or encountering it. You'll probably come across aircraft that has your AC systems and stuff that you have to mess with. They generally don't have to get a whole lot of work done to them. Just in general, they just don't get used like an HVAC system or the system on your car or anything else like that. But if you do, this is what you'll end up having to contend with. Okay, this is a vacuum pump. You should be really familiar with the idea of a vacuum pump, at least, because we mess with them in composites. There's not really just a whole lot different between the two. Essentially, what you're going to use a vacuum pump for is you're going to hook it up to the system, and you're going to pull a vacuum on that entire system. You're going to pull everything, every bit of air, old refrigerant, and everything out of that system, so that way you have this like intense vacuum that's happening, so that when you introduce the refrigerant into it, it goes throughout the whole system like in the blink of an eye. And that's what you use vacuum pumps for. But if you're having to charge a whole system for the first time or install one, this is something you'll have to use. It's no different than the vacuum pumps that we use here, or that you would use it on a composites job. Basically the exact same thing. Maybe there might be a slight difference in fittings because on one you're hooking up to a vacuum bag, and the other one you're hooking up to a AC system. But they do the exact same job. Okay, other types of maintenance that you may end up having to do, you're going to do a lot of inspecting of AC systems whenever they're installed. What you'll end up doing is a lot of general visual inspections. Just like you're looking for any kind of rupture to the system. You might end up doing a MOC or a bite test of some variety. And you also take one like a tool like this or something similar to it, and literally look at the system looking for leaks. Now, this is kind of a sniffer that detects your coolant leak coming out. You can also take a FLIR gun and just point it, because as the coolant leak comes out, even if it's really, really small, it's going to super chill the area that it's coming out of. And then whenever you get that, you'll get a either a white hot or black hot, depending on how it's set up, spot on the system that'll look fundamentally different, especially after it's sat for a long period of time. And you'll know that there is a leak there. Now, these systems don't have a whole lot of refrigerant in them to begin with. I mean, you think like a 12-ounce can could, in theory, top a system off totally. And so a little leak goes a long way in terms of like damaging the system. So just something to keep in mind. But there are special tools out there. You don't necessarily need them per se, because there's a lot of people that get by without them. But they are super helpful if you can get your hands on them. Okay, condensers are kind of a weak link in the world of AC systems. So these coil fins are there to help radiate that heat and return the expanded refrigerant back to being a liquid. Uh, Now the problem with this is that they have to be so thin in order to effectively radiate it that they're also extremely susceptible to damage. Um, this is really easy to see. You just go check your HVAC system at your house and look and see anytime that anything so much as barely touched it, it'll bend it. Now this can be a source of leaks. If the damage is significant enough. And generally speaking, on an aircraft, they're going to be like in an avionics or equipment compartment that's kind of away from everything to try to prevent this exact thing from happening. But condensers are something that you need to pay attention to, where it could be susceptible to damage and the source of leaks. And this is what a damaged condenser fin will look like. Now, we talked a lot about heat. Let's talk about cooling. Now, one of the things that you have to keep in mind is that as aircraft continually get more and more technological, more and more computers get integrated into the system, so specifically the displays. Like, what happens whenever that instrument gets too hot? Let's say you're in the Mojave Desert and you crank up your new Cessna 206 with a G1000 on it. You're super excited, but the heat is just too much for that computer. What systems are available to help bring that temperature back down so it'll be cooled off? Now, when I was in the Army, we used to regularly make fun of the Apache guys. They would always act like they are, Maverick from Top Gun, but we would always point out that even though we were in the middle of a desert war, they were the only airframe that had a air conditioner on board, and it was actually cool to sit in their cockpit, as opposed to any of the other airframes where you were baking to death. Now, that was all right and just to make fun of the Apache guys and try to get under their skin because of the sibling rivalry that exists between airframes. But one of the things that I don't think people appreciated was the level of avionics that actually are on board an Apache attack helicopter. And it's a lot. They have some pretty advanced systems. They can do any number of things, and all of which require these little black boxes that are stored throughout the aircraft that have to be maintained at a certain temperature. If the temperature gets too high or too low, the boxes start to malfunction and the aircraft doesn't work properly and may not even fly at all. And so that aircraft was equipped with its own air conditioner to keep those avionics cool. Now, fast and forward a few years, I'm working at ATS up in Everett, Washington, on a Virgin American plane, and we had a situation with this particular airframe. They were troubleshooting a radio problem, and we noticed that the longer that the aircraft ran, the worse the problem got, and the new problems would even start to crop up. And then we realized it was that because we didn't have a huffer cart hooked up to it to move air around it or anything else like that, we weren't running packs or any number of air sources. The airplane would just get hotter and hotter and hotter and hotter, and it would start to cause problems. Now, as that problem would happen, what we would do is we would shut the aircraft down, we'd let it cool off, and we'd turn it back on. That's what I called the Airbus reset. It was like kind of Control Alt Delete, and all your avionics problems goes away. But what was really happening is that you're letting the aircraft cool down, so that way you don't have so many issues with your avionics. And that's all instrument cooling really is that your computers are built to operate at a certain temperature at all times, like room temperature. And then there's a range and there's tolerances like anything else, but really it can only take certain levels of extremes, and if it gets too hot, then you're going to start to have errors. So temperature cooling is absolutely, or equipment cooling is absolutely essential to proper operations of any avionics suite that's out there. Now, equipment cooling on your 737 works like this. There are two fans that can work in the normal and alternating mode, and I will tell you they are very loud. If you're up in the eBay, you might as well just wear some earplugs or at least like a headset with radio capability, so that way you can talk to other people, because it's going to scream at you. It's just going to go it's super duper loud. And what that's doing is it's moving air through the eBay and through the channels on the ear racks. Now, There's those are the backup fans. You also have your normal environmental system air that they'll come through there and it'll move heat off those boxes. But the whole point is that you can run the equipment while the aircraft's on the ground basically indefinitely because those fans were allowed. Or will move air and keep them cool, and so it's extremely important. Now, every aircraft that you come across should have some sort of equipment cooling approach to it. Some of the smaller GA aircraft with like an advanced avionics, so you look at my plane, I'm looking to put a Dynon panel in it. Those panels need to be kept cool in all the boxes as well. But I don't have the resources or the space, or really, I don't think there's even an STC for an equipment cooling capability that goes into it. So you just have to be really mindful of the way that they get used and operated and stored. And so like that's something you need to put in your your pocket for like troubleshooting if there's a bunch of issues and you get out there and the aircraft is just sitting there baking on the flight line. Like maybe the first thing to do is just get in the hangar, let it cool down, and then turn it back on and see if it all works. If that doesn't solve it, then maybe there's other issues. But especially if it's like really bogus, weird stuff that doesn't seem to track any kind of like logical way, it could just be that the aircraft has gotten too hot and it just needs to cool down and then turn back on and try again. Not too unlike people will get hot and start being kind of crazy. Aircraft will get too hot and start being crazy. So the main thing is you want to keep those equipment cool as best as possible because it's really important for the proper working of your avionics package.